Well, thanks very much, Clive, and many thanks to Affinity for inviting me to come along and talk to you about probably my favorite topic to talk about, which is the Anthropocene. So we will dive in straight away. And have we got it up? There we go. So I'm going to be talking about what the risks of this new age of humans really entail, what our challenges are, and the critical choices that we need to make. A lot of my talk will be organized around this concept, which is our home planet. And the point I want to make is it is a single system at the planetary level. You may have heard about all sorts of systems like the hydrological system or the climate system or social systems. But we're all part of one system, the Earth system. And so that is a reasonably recent concept, but it is one that is very important for understanding what's happening to our home planet. We can go down to Antarctica. In fact, those strip of photos on the left come from Australian Antarctic territory. Drill down into the ice. You can go several kilometers down into the ice, and you can extrude out cores of ice like this, which are beautifully layered, layer by layer by layer. And by studying those, we can piece together a history of Earth. Here's an example. This goes back 400,000 years, not 400, 400,000 years. And this red jagged line is Earth's average temperature, or I should say the average temperature over the South Pole, which averaged over a large period of time is the same as the Earth's. And you can see a very irregular pattern, not unlike a human heartbeat, in terms of warm periods, very short, about every 100,000 years, and these long, jagged ice ages. And that is symptomatic of a complex single system. Look at the boundaries, always the same, just like your blood pressure. Look at the pacing, always the same, just like your heartbeat. And it's been doing this for about 1.2 million years. But the geneticists tell us that we, Homo sapiens, came around this planet about 250,000 years ago. And this has been our home. This is what we live in. This is what we are adapted to. But through two of these ice ages, we were only hunter-gatherer societies everywhere around the planet. And that's because this climate is a very cold one. It's less wet, it's drier, and it's very erratic. But this last warm period of about 11,700 years has been a planetary sweet spot for us. So if I look at that in more detail, there's the last 100,000 years, the previous ice age, very sharp warming by geological standards. That took about 7,000 years. And now we have natural variability, but it's very steady compared to an ice age. So this has allowed humanity to develop agriculture, starting about here, and then we've developed increasingly more complex societies, more complex technologies, until here we sit in 2018 with a very highly globalized, highly technical society. The geologists call this last nearly 12,000 years the Holocene. What came before it is called the Pleistocene. So the Anthropocene obviously is the next stage of what's happening here. But of course this pattern here is driven by natural forces. The trigger is the Earth's orbit around the sun, subtle differences. The heavy lifting is done internally in our own system, done mainly by two things: outgassing of carbon dioxide from the ocean as it warms, and of course carbon dioxide is a greenhouse gas, so it warms the planet, and the shrinkage of ice as it gets warm. And therefore we absorb more sunlight, and that heats the Earth too. So we know what's going on really well. So back in the year 2000, 2001, a group of us started to think about how we could document how Earth was changing. We updated these graphs in 2015. I was the lead of the group that did that. And so we asked ourselves, if you had a limited number of indicators that described humanity as a whole, what would they be? So we used, obviously, population, economy, there's energy use, urbanization, and here we have some resource use, and here we have some transport and communication. And so we started these graphs at the year 1750. because a lot of scientists were saying things changed with the Industrial Revolution. And of course, the Industrial Revolution started in England in the 1780s and then spread around the world in the subsequent century or so. And so we got the data, we plotted them, and we were really surprised. We expected a nice smooth line from 1750 to 2010. We didn't get that at all. Not much happened at all until 1950, middle of the 20th century. And then everything just took off, exploded around the Earth. Even population increased in its rate. Certainly economy did, certainly energy, certainly resource use, and certainly communication. And some of them, of course, waited until the invention of mobile technologies. So we nicknamed this the Great Acceleration from 1950 onwards. And of course, a lot of economists would tell us, this is fantastic, this is progress. This is what we should be doing. But then a lot of my colleagues who are in the natural sciences said, wait a minute, we better see if there's any trace of this sort of pattern on the Earth. So we did the same thing for what we call the Earth system. And here you have those trends. The top 6 are what we call the geosphere, the non-living part of Earth. So you have the atmospheric gases. There's carbon dioxide, the famous one up in upper left, the stratosphere, the climate system, and the ocean. The bottom 6 are life on the planet. So here we have the ocean, the coast, and the land. So again, here we have 12 indicators, and look, we have a pretty similar pattern. Not exactly identical, but it's remarkable that they're all swinging upwards, whatever indicator we use. And for many of them, 1950 seems to be a pretty significant date, which obviously suggests a connection between what humans are doing and what's happening to the stability of the Earth. 2 things we can say about these graphs. Number one, we can say that where we sit in 2010, which is the last year we had all this data, we are outside of the Holocene. We know what the Holocene looks like for the last 11,700 years. So this is the most coherent single piece of evidence that tells us we're actually in something new. We're not in the Holocene anymore. We've left it. The second thing we can say for sure is a massive amount of scientific evidence. Each one of these is driven primarily by human activities, often quite directly. They're outside the bounds of natural variability of the Holocene, and they are not natural variability themselves. It's not a change in the Earth's orbit or a meteorite strike. It's humanity that's driving this. So therefore, we call it the Anthropocene. There's a good way of visualizing this, and this was done by National Geographic in 2011. And that's to say, if we simplify the Great Acceleration, humanity, into 3 drivers, what would they be? Well, they would be population, affluence, which influences how much we consume, and technology. How do we make the stuff that we consume? Because you can have better or worse technologies. And so what we tried to do was take those 3, and of course they form a box. So here is technology, here is population, and there is affluence. We make a box, and we fill it with stuff we consume, fridges, airplanes, cars, etc. And so National Geographic wanted to go from 1900 to 2011. So this little box, just there, that's 1900. And then they have 2011 as the whole box. And they sent it to me as an advisor on this piece in National Geographic. And they thought this was fantastic. And I said, this is terrible. You've missed the whole story. And they said, what? What have we done wrong? And I said, well, you'd have them put in 1950. And of course, they hadn't read our scientific papers. I wouldn't have expected them to. And so they said, well, why should we put it in? It would be halfway up. And that's not going to add anything. And I just wrote back and said, put it in and you'll see. And they put it in and they were shocked. There's 1950. So there's half a century, 1950, and then the next 50 or 60 years. Explosion. That's the Great Acceleration. They were shocked, and then they said, I see what you were saying, while we put in 1950. Now, the origin of the term actually goes to this gentleman here. This is Paul Crutzen, a Dutch scientist, atmospheric chemist. He is a Nobel laureate, not for the Anthropocene. He got it earlier. He was one of the scientists who worked out what was happening with the ozone hole, and that in fact it was our CFCs, chlorofluorocarbons that we were using for refrigerants that was causing the problem. But he was at a meeting in 2000, before we published these graphs, But he was hearing reports from scientists from different disciplines talking about how the Earth was changing. And they kept referencing the Holocene. And he got really angry. He said, hey, listen, people, we're not in the Holocene anymore. And then he just used the word for the first time. We're in the Anthropocene, being a new geological epoch, one caused by humans. So let's now focus in about what everyone's talking about, climate change. It's an important part of the Anthropocene narrative because the climate system is really an important part of the broader Earth system. So here is the modern instrumental record of global average surface temperature starting from about 1880 when we had enough modern instrumentation around the planet to get a global average. And here we are in the last few years. And you can see how remarkable that is. Again, here's 1950. You can see some rise there, but it really takes off from about the middle of the 20th century. We stand about 1.1 degrees above pre-industrial. Doesn't sound like much, but in terms of global average temperature, the difference between an ice age and a warm period is about 4. So we are already a bit more than a quarter of the way to that same 7,000-year difference. We've done this basically in a century. So I'll get on to the rates in just a moment. But even more impressive is if you look at the background rate of change. There's AD 0, 2,000 years ago. And here we are today. The climate is naturally variable. So there's global average temperature. It wiggles ups and downs and so on. But within the bounds of these two blue lines. And those are basically determined by Earth's orbital parameters. The Earth wobbles a little bit, and of course its orbit isn't circular. But we can calculate all that and work out what the climate should be doing. And indeed, it behaves really well, exactly as we expect, until here. And then it shoots up. And of course, that's the greenhouse gas emissions from the Industrial Revolution and onwards. This is the human influence. And so this is now about 1 degree above that. These are in tenths of a degree over here. But even more striking is the speed at which this is happening. This is an enormously fast rate of change. So when we compare that, since 1970, the global average temperature has risen at a rate about 170 times faster than that background rate. Over the last 7,000 years, actually, of the Holocene. And in the opposite direction, there's been a very, very slow cooling trend since the so-called mid-Holocene. CO2, the rate of CO2 increase itself is rising. And over the past 2 decades, it's about 100 times faster than when CO2 came up from the last deglaciation. So again, that's extremely fast. Ocean acidification I haven't talked about, and I'll just mention it briefly. The CO2 we release, primarily from fossil fuels, doesn't all stay in the atmosphere. The Earth is a system, and it tries to self-regulate. So half of it's absorbed. And of that half, about half is on the land, and half is the ocean. So that's a good thing, because it takes half of our emissions out of the atmosphere. But that quarter that's absorbed by the ocean forms carbonic acid. If you've done first-year chemistry, you put CO2 in water, it forms H2CO3, carbonic acid. And that's not so good for the marine biology. And it's gone up and down for natural reasons in the past, but never at the rate it is now, at least as we can see for the last 300 million years. So this is a very, very long period of time. And so the ocean biota is getting hit with something it hasn't seen for a long, long, long time. What do we feel in terms of the rate of change? This is how it's expressed in Australia. These are all photos from the last 10 years. They're all photos from Australia, and every one of them is outside of the norm as far back as we can see, both from paleo records and from our instrumental records. So we have excess heat, extreme drought, storms, bleaching of the Great Barrier Reef, fires. It's not surprising this is happening. When you hit the Earth system with a rate of change this fast, it's going to respond, and it's going to respond in ways like this. So we have strong evidence that in all of these cases, this isn't natural variability. This is a climate on steroids, and we are the ones feeding the steroids to the climate. Okay, I've talked a lot about the climate, but the Earth also is a beautiful planet because of life, that beautiful life on the planet. And of course, we're part of that. We are embedded in what we call the biosphere. And it's interesting that the biosphere has actually been an active player in helping to regulate the Earth. It does it by absorbing carbon. It does it by providing oxygen for the atmosphere. In fact, the reason we have oxygen we can breathe is because of the marine biota, which changed the Earth's atmosphere from one that had very little oxygen to one that has 20% and we can breathe. So life is really important in general. We've had 5 mass extinction events in Earth history, but we're on the way to the 6th. A mass extinction event is defined when 75% of species of major types of life go extinct. The last one was 66 million years ago when a meteorite hit the Earth and wiped out the dinosaurs. And that allowed the space for mammals to really take over the planet, which we have. But we see now, today, that either already extinct or threatened throughout all these types of species, we are pushing that rate up. So we haven't yet hit the 6th great extinction event, but our rates are tens to 100s of times higher than the background rate of extinction. And at the present rates, by the time my grandchildren, I hope I have grandchildren soon, by the time my grandchildren are up to my age, we could in fact be declaring the 6th great extinction event, unless we change what we're doing. And that's direct, that's not climate change, that's direct human pressure on the biosphere, mainly through land clearing, through pollutants, through plastics, through all sorts of things like this. This is one that I found when I first saw this, a staggering statistic. What this is, terrestrial vertebrate biomass. What are vertebrates? They're everything that has a backbone. And what's terrestrial? That's land. So there's 4 types of creatures. There's mammals, like us. There's reptiles, there's amphibians, and there are birds. And you just add up the weight of all those creatures, the whole lot of them. Nearly a third is just us. My 70 kilograms plus all of yours plus 7.5 billion people. We comprise about a third of the mass of all creatures on land. But our domesticates, pigs, chooks, cattle, another 65%. When you add that up, you got 3% that's wild creatures. So we still get these travel brochures with all these wildebeest and things from Africa. Tiny, tiny fraction of life on land. Almost all of it is us and the stuff we raise to eat. Okay. The Anthropocene is a geological sounding term, so it took the geologists, they really look at the planet in a slow way. I mean, 100 million years is really fast for them. So it's not surprising that they didn't jump onto the Anthropocene straight away. So they worked really fast, though. It took them 10 years before they said, oh, wait a minute, these guys are running around and saying Anthropocene. Maybe we should do something about this. So they formed an Anthropocene working group, and they were really kind enough to invite a few of us non-geologists onto it. So I'm one of them. It's really fun watching them work, digging down into the ground and so on. But they're really methodical, very, very careful. And they asked themselves this question: have humans changed the Earth system such that geological deposits forming now and in the recent past include a fingerprint distinct from that of the Holocene? So they've got to see something different when they dig down and do their cores. And if so, when has the change become recognizable worldwide? That's what they look for, to declare this officially as a new epoch. Jan Zalasiewicz is the convener of this. He's doing a fantastic job herding the cats and getting us to work together. Here's our conclusion so far. In the stratigraphic record, we can already see signatures of human origin, and they're well above the Holocene norms, and will leave a lasting signature. So we can see humanity writ large in the stratigraphic signature already. Evidence is most consistent, not surprisingly, with mid-20th century, great acceleration. And now we're looking at specific cores for formal proposal to the parent body. What are we actually seeing in the cores? Here's some of the stuff: aluminium, concrete, plastics, synthetic fibers, nitrates, radioactive nuclides. And look at what they look like. It's 1950. It's quite remarkable. And they're synchronous around the planet. You see them everywhere, every continent, ocean basins. Plastics have been in the news recently. You see them everywhere, middle of the Pacific, down in Antarctica. And that's because, of course, the atmosphere and the ocean mix things. So there we go. This is some of the evidence that's going to be put forward. Earth system perspective. If I now go back and say this is a single system, how can we actually describe what's going on? That's the graph I already showed you. But what does this actually look like when we go forward? This is what you see from the IPCC. These are climate models. So we're sitting about here. Low emissions and high emissions, and there's some in between. Models are pretty good at doing this. So here we are, 2100. My granddaughter or grandsons will hopefully be around then, and they might experience something in through here. But what does that look like in an Earth system perspective? So what we have to do is take this spike, that's the current temperature rise, and put the projections out onto it. There's 1900, 2000, 2100's here. When you do that, it looks like this. There's the Paris target, 1.5 to 2. There's 4 to 5. If everyone adopted our federal government's policies of today, we'd be at 5 degrees Celsius by 2100. So you can see how dramatic that is. We're pretty much committed to a 2-degree temperature rise. And that's in the pipeline because we can't get emissions to zero by tomorrow. It's going to take us a few decades. And of course, if we do the worst case scenario, that's a completely different state of the Earth system. It's as big as the difference between an ice age and a warm period, which would be 4 degrees down this way. So it's just a completely different Earth, one that we don't recognize. But to go there in a century and a half is going to challenge even highly technological modern societies. Some of our recent work says that we're not just going to go to any one of these things, that the Earth, of course, is a system, and it behaves as a system that has well-defined states and transitions. So our challenge, if we meet the Paris target, is to maintain the Earth in what we might call a Holocene-like state, warmer, but something that we might recognize. But if we go to the worst-case scenario, this is a transition to a new, much hotter state of the Earth system, and we're arguing that you may not get much in between, that there are tipping points that are inbuilt in the Earth system, that once you activate them, sort of like a row of dominoes, you start tipping them and they tip and tip and tip, until you tip them and then you're in a hotter state. Now, we actually know an awful lot about this. These are what they look like, and you see that some of them in green are big biomes, part of the biosphere that can tip, like the Amazon forest. If it gets too hot and dry, it burns and it changes into a savanna, an Australian landscape. And we can melt ice, West Antarctic ice sheet, Greenland, permafrost, and so on. There's a whole range of these. And we actually see them starting to change. 2 years of drought, big fires in the Amazon, we've lost 10 years of carbon storage. That happened in 2015, 2010. There was another big one in 2015-16. We could lose anywhere from 50 to 250, that's billion tons of carbon, permafrost melt up in Siberia. And again, that's experiencing more than average warming, and we're starting to see bubbling of methane out of that already. Arctic sea ice, we think we've crossed the tipping point there already at 1 degree. So by summertime, that'll be ice-free in another decade or two. And of course, the Russians and others are already lining up to drill a seabed for oil in there. Coral reefs, I don't need to tell you what's happening to them. Some people think we've already crossed a tipping point for them. We won't get them back. Greenland, that's surprising people. That's a thick ice sheet, but that line shows the rate at which it's losing ice, which is increasing with time over the last couple of decades. Perhaps even more surprising is Antarctica is starting to move too. We're starting to lose ice from Antarctica. And of course, these things raise sea level, and those ones up the top, once that ice disappears, then you have much darker ocean water or land that absorbs more sunlight, heats it even more. So these are what we call reinforcing feedbacks. And this is our dominoes. So we made a little map and put arrows and said, if you line them up like dominoes, some of them start tipping at 1 or 2 degrees, they tip some at 3 degrees, and the whole thing goes over. So we just published a paper very recently, and we made this little thing. It's a little bit hard to understand, but this is what we call a stability landscape. Think of a marble rolling around an uneven tabletop. So this is our glacial. These are our ice ages. That's the Holocene. That's a warm period. So the Earth, every 100,000 years, rolls up, sits here in this little shallow basin, and then the Earth's orbit changes and it rolls back down. It does this rhythmically. But humans now have put so much CO2 in the atmosphere that we're now over here in some new forming basin that doesn't exist there actually naturally. We think the one that's natural is actually way down here. And that's after you tip all the dominoes. So we're sitting here about 1 to 1.1, 1.2, and we're in the Anthropocene. And once we came out of that basin and started over here, we left the Holocene. So somewhere in here is about 1950. Here we are in 2018. And now we got some choices. Because we're in the driver's seat now of where the Earth goes. If we get our emissions down and meet the Paris targets and take much better care of our biosphere, protect Amazon, protect a lot of the natural ecosystems, we call it stewardship, which I think is a really nice word because we need to be stewards of this beautiful planet that we're on. Then we can sort of park the Earth in what we call stabilized Earth. 2 degrees warmer, a much more resilient biosphere, and a much more resilient, probably more equitable human society as well. Now, this is not a natural valley. This is one that's created and maintained by humans. So that's what we have to really understand, is that if we stop all our pressure, we're not actually going to go back to where we came from. We've left that. So we've got to think really carefully of where we want to go. If we keep degrading the biosphere and keep emitting greenhouse gases, this pack of dominoes could act like a cliff in our landscape. And once our marble rolls down and down and over the cliff, you actually can't get it back. And it's not a place you want to be. So this is really the choice we face now. And it's important that I think this fork in the road could come actually within the next decade or so, given our emission rate. So we've got some choices to make. And that's why we can't wait for the next electoral cycle. We've got to push politicians of all stripes to say, put your differences down. This is really important. We've got to do the right thing by the planet we operate, or we'll suffer the consequences. So that bit there is our glacial interglacial cycling. That bit there is the spike of temperature that we're at now. And this planetary threshold, that's our dominoes that we go across. So this is a really intuitively easy way to understand this, is our marble rolling around this landscape. And we're now in the process of forming this landscape ourselves. Well, is this really plausible, all this stuff? We just published it about a month ago. Yes, it is, because if we look in the recent past of Earth history, we find times when concentrations, currently it's about 400 parts per million of CO2. 3-4 million years ago, it was called the mid-Pliocene. It was also 400 to 450. Temperature was 2 to 3 degrees higher. Sea level was 10 to 20 meters higher when it eventually equilibrated. Different world. If we go over the cliff, we get to what we call the mid-Miocene. So we know the Earth can actually do this. The Earth knows how to live in these conditions. That's up to 500 parts per million. 4 to 5 degrees, as we put on the graph. Big estimates, big range for sea level, 10 to 60. 60 means you eliminate virtually all the ice on the planet. So that's the sort of futures we may look at. How plausible? Well, we know the Earth acts as a complex system. We could see that in the glacial interglacial cycling. We know that these hothouse Earth conditions are accessible with the CO2 and temperature that are projected by the short-term climate models this century. We know the feedback processes. We've seen them operate in the past, so that's not fanciful. And some observations are already showing tipping elements vulnerable at 1 to 3. So we've published this. We got it through the review process. It's out in the literature now. Hopefully it's going to trigger more debate amongst the research community about how dangerous this is. We can't actually put a number on the probability or where exactly that cliff lies, and that's the next thing science has to do. All right, I've talked a lot about the climate system and the biosphere. I'm going to end a little bit about talking about humans, drawing on work of other people. I'm a natural scientist by training, but we humans now are a completely important part of the Earth system. So we shouldn't look at ourselves as something outside. We are part of the Earth system, part of the biosphere, influencing the climate system. Well, the first thing is a couple of Swedish colleagues said, hey, wait a minute. You guys, you natural scientists talk about humankind or mankind in general. They said that's wrong. He said the Anthropocene wasn't driven by all 7 billion people on the planet. It was driven by the fossil fuel-driven, consumption-oriented, globalized economy. That's what drove it. And so you've got to take into account inequalities amongst and across human societies. We were challenged, so we said, all right, let's go back and do something about that. Let's look at those 12 graphs and start splitting them up. That's what we did. We didn't have data for 2 of them. We got 10 of them. So the dark orange is OECD. That's the wealthy countries like us, New Zealand, Japan, Europe, United States, of course, and Canada. Then we have the BRICS. Those are the rapidly emerging economies of China, India, South Africa, Brazil, and so on. And the light ones are all the others, the poor countries. So all you got to do is look at the first two up here. Population from 1950, almost all of it's been in the BRICS and the poor countries. We've added only a little in ours. But in terms of GDP, which scales with consumption, we still account for 75% of the global consumption. So huge inequalities across the planet. So they were right. Our Swedish colleagues were right, and so we had to admit that we really should do this. When you look at resource use, you start to see China really emerging here, and India, fertilizer and water and so on, as they grow food for very large populations. But when you look at the OECD countries, everything isn't rosy here either. And some of my colleagues in the social sciences who work on equity issues said, you really got to look at what's happening in the wealthy countries. And this is all from the United States in the last decade or so. And the thing they're increasingly pointing to is equity, or really equality. So here's income inequality. So this is how much of a country's income the top 1% take. So here you see huge inequality back in the early 1900s. This is leading up to the First World War, Great Depression, Second World War. That equalized everything out. And here we have around 1940, 50, much better equality right across, whether it's the English-speaking world or the Europeans. But look what's happened recently. Europeans have kept pretty much the same level of equality, income equality in their societies. Not so in the English-speaking world. There's a big divergence between our countries and the Europeans. Here's the USA. It's almost as bad as it was during the Roaring '20s, leading up to the stock market crash and the Great Depression. We are the best of the English-speaking world, but we're still creeping up. So I think Australia can be, in a way, proud of the fact that we're the closest to operating like the Europeans in terms of income inequality. But as you all know, we still have some issues coming in. And the interesting thing is, this actually matters for our societies, because when you look at income inequality where it's high, and then you look at social problems, they scale. All of these are wealthy countries, so poverty is not an issue. Equality is an issue. And so those with the most unequal income distributions have the most social problems. The US is way up the top, the worst by far. But most of the English-speaking countries are at the top. Here we are, New Zealand, UK, Canada's the best. What countries come out best? Nordics and Japan. So income inequality matters for social well-being. Now, as an Earth system scientist, I do a lot of work now with social scientists, but I try to always put it in a system framework. And so what I'm seeing with the Earth system now is we've got some big system incompatibilities in the human side, in the biosphere, and so on. Again, don't need to tell you where that comes from. But if you look at the geosphere, beautiful circulation patterns of the planet. That's the ocean, atmosphere as well. But we are superimposing a massive circulation pattern on top of that in terms of movement of people, goods, energy, and so on around the planet. That's a human-driven global circulation pattern. A lot of people think that's what the land, most of it looks like. Nope. Increasingly it looks like this, human-dominated landscape. And what about the human side? Well, we're doing really well, in a way, in getting people out of poverty. That's actually moving pretty well, although it appears to be stalling. About 800 million out of the 7.5 billion of us are still really poor and malnourished. But the interesting thing is, over 2 billion of us, almost all living in cities, are obese, overweight, or have micronutrient deficiencies. That's a much bigger problem now than malnutrition. So again, big incompatibilities in our system. Some of you may know this guy, Clive Hamilton, very outspoken guy, and he's done a lot of work on the Anthropocene, the fate of humans in the Anthropocene. And so he looks at these incompatibilities, and Clive's always provocative. And one of the things I picked up was this comment he made, that the force of the consumer culture, which is sort of taking over the planet. And all the traditional values we have and aspirations are being replaced by a devotion to money, materialism, and branded identities that has left tradition in a smoking rubble. This is a really good book, The System's View of Life, A Unifying Vision, which is really beautifully written by two gentlemen there, Copper and Louisi. And then make a really interesting comment too. Our world today is dominated by a global economic system with disastrous consequences. They call it predatory capitalism because it exploits rather than regenerates and doesn't act as a steward. We're the only species that knows who destroys our own habitat. No other species actually knowingly does that. And of course, we're driving many others to extinction. And of course, there have been some books coming out looking at the type of capitalism we have today, neoliberal capitalism. And Thomas Piketty has written a famous one about that's what's actually driving this inequality. It's not evil people. It's a system property. And that's really something we've got to get through. Instead of blaming people, we need to look at the underlying systems that people are embedded in. Same thing with climate disruption. And extreme wealth corrupts political systems. This is the story of the petrochemical industry in the United States, the Koch brothers and so on, who have distorted that political system. And we can see it here, obviously, in Australia as well. Another beautiful book, Donut Economics. There are some really smart people out there that say, hey, we've got some new ways of thinking. We can solve this, but we've got to change. This is one of the best. Kate Raworth, she's an economist at Oxford. She's come up with this donut idea, where really how you want to organize our societies and our economies is you need a floor, a foundation of social well-being. If you don't have that, you're not going to have a good society. So it's obviously you need food, water, education, resilience, but you need equity, gender equality, health, jobs. You have to have a society that's really running well in terms of human well-being. At the same time, you've got to do it staying within the ceiling, the planetary boundaries of keeping the Earth in a stable state. And of course, this is where we come in, we natural scientists, because we can talk about what are the boundaries we need to respect. She gives 7 principles. I've only got 3 here because I think these stood out to me. Systems thinking, not linear dynamics, systems thinking, dynamic complexity. Equity. We actually have to have an economic system that is distributive by design. The one we have now accumulates and amasses wealth in smaller and smaller groups of people. We need it the other way around. It needs to be distributive by design, and it needs to be regenerative, not exploitative, concerning the biosphere. And she has some really clever ways of how we could do that when you dig into it. So there are some really innovative thinkers out there. So our challenge really is to look at this triple bottom line, which we write, but in fact, in reality, it looks like this most of the time. We need to rebalance that, of course, as we go forward. I'll just close with some philosophers. This is Dipesh Chakrabarty. He's written a lot about the Anthropocene, and he comes, of course, from the Indian culture, which has a very long culture as well. And he said, look, here's our problem. In the last couple hundred years, we've become human-centric, and we really should be life-centric. And that's actually quite different. And so we've got this human-centric approach, but the Anthropocene is the big warning sign to say, wait a minute, this isn't the right path. We need to be a zoa, a life-centric approach. And he uses some nice terms. He said, we're stuck in departmental thinking. We separate everything out. We need an epochal consciousness. Carl Folke, a colleague of mine, says it in 4 words. We need to reconnect to the biosphere, the rest of life, and so on. But I'll give the final word to our indigenous colleagues who actually know how to do this. By the way, do you realize that indigenous Australian people have the longest continuous culture on the planet? The only ones that went through the Ice Age warm period transition intact. And they did it on the toughest continent on the planet. It's a pretty good track record. But here's an elder from WA, and she said very clearly, look, here's what we're to do. We have to look after the country. We're a tool in the cycle of things. They understood systems. We go out into the world and help keep the balance of nature. It's a big cycle of living with the land and then eventually going back to it. So I'll leave you with some things to think about, and hopefully I haven't taken up too much time. Maybe we have time for some discussion and questions. So.